Thinking in C, Chapter 8b, Pointers 102. This is the chapter that has everything else in it that you don't need if you are going on to Java. So if you're going on to C++, well, this is for you, and that's why all this stuff is in there. Most of it is on pointers, but in the first section, I'll cover a few things that are important but really are not pointer related. The non-pointer things that I need to cover are unsigned integers and type-def. We've talked a little bit about unsigned, but haven't been real explicit, and I'd like to do that now. Each of the different integral types in C have an unsigned version. They're signed if you just use them like int is the same as signed int. The only exception to that is char. Whether a char is signed or unsigned depends on the platform, but usually you just don't worry about that. Anyway, if you put an unsigned in front of any of the other types, unsigned int, unsigned long, unsigned short, well, that makes it so that the most significant bit is not used as a signed bit. Therefore, you have one more bit that you can use for your value. So your numbers can go between 0 and 2 to the appropriate power. So, for example, if you have a short, which is 16 bits, then you can go to 2 to the 16th minus 1 as your maximum and 0 as your minimum. So basically, it's just taking those numbers that the signed integers comprised and just moving it up to where the smallest one is 0 and the largest one is the one I just mentioned. You saw earlier in a previous chapter the term size t. Well, size t is defined to be an unsigned integer type, usually unsigned int. And we're going to learn in a minute how we can actually define a new type name like this. But size t is that thing that is used to hold things like array indices or anything that's a size type of thing. This little program uses limits.h to print out the unsigned limits. Of course, there's no min because min is always 0 for the unsigned, so there's just a max. And so here are the maximum values on my platform for character, short, int, and long unsigned versions. This example shows you the effect of declaring something unsigned when it comes to bit operations. In particular, we're talking about the shift-right operation. You may recall that we talked a little about sign extension way back in the operators chapter. Whenever you shift an integer to the right, it propagates its sign bit. I'm about to prove that right now. I've declared here, well, this is very similar to that same program we had a long time ago. The only difference between the declarations here and what you've seen before is the introduction of the word unsigned for n. So n is unsigned, m is not unsigned, it's a signed integer. And let's take a look at the differences here. Now, when I use the complement operator, tilde, to flip all of the bits, then that, of course, makes all the ones that were 0 ones, and that's why all those f's are there for both n and m when you flip them. But now, take a look what happens when I take that result, the ones complement of n, and shift it to the right 4 bit positions. That third line of output will show you that I got zeros. But when I do the same thing for m, which is signed, it did propagate the sign bit as things were shifted to the right. So that is the main difference between signed and unsigned as far as bitwise operations are concerned. If you want to propagate a 0 instead of the sign bit as you shift to the right, you declare the integer unsigned. And that's what it will do. Otherwise, it'll do the normal sign extension. Now, how is it that I can have something like size t, but it's really just an unsigned int? Well, what I'm saying is that size t is a synonym for unsigned int. It's not a separate type, it's just another name for the same type. Well, there's a facility in the language called type-def, which stands for type definition, and it allows you to declare these synonyms. So for example, to do size t, it would be something like this statement that you see here. Type def unsigned int size t. Now, the way you read this and understand it is forget about the type def just for a moment. Put your finger over that or whatever it takes, and you'll see unsigned int size t. Now, if that were a normal declaration, then that means that size t would just be a variable of type unsigned int. Well, now you take your finger off and let the type def come back, and what the type def does is it makes what would have been a variable without the type def to become the synonym for the new type. So size t is the same thing as unsigned int. So the target is whatever is in the variable position. Not only do we use it as an abstraction mechanism like this, but sometimes it comes in handy as a shorthand. In other words, you can have a type declaration which is kind of long. It has a lot of words in it, and maybe it is just too much to type. And if it's complicated and you're tired of typing it all the time, well, then what you can do is give it a new name and make it short. And that new name becomes a synonym for the complicated type declaration. Well, the way we're going to illustrate that for now is we're going to get rid of the keyword struct. You know how we've had to keep typing struct for struct employee or struct hitter or whatever, because struct is part of the type name. Well, what we'll do is we'll just shorten that by just making up some other name. This little trick we're about to show in the next slide actually is implicit in C++. It's done for you, so you don't have to keep typing struct all the time. But in C, you've got to do this type def trick to get the shorthand. Well, here's that trick, so you don't have to type struct. Given a struct definition, for example, here I have struct foo. It has two integers inside of it. If I have the type def statement which says type def struct foo, then that last instance of foo, which is my target, or which would be my variable name if I wasn't using the type def, that becomes the name of the new type. So instead of struct foo, I can just type foo. You're probably wondering, gee, how does the compiler keep that straight? Well, it just does. They're actually different namespaces. Struct tags are in their own namespace in C, and so there's no confusion with the struct tag foo, which is used with the struct keyword, and this type def that you define. So once you do this, from then on out, you can just say foo. And it's the same as if you had said struct foo. Well, that's enough odds and ends. Let's get back to pointers. Since pointers can point to anything, that is any valid type, it turns out that pointers can also point to other pointer types. And sometimes you want to do that. It turns out you can actually get pretty complicated with this. The standard says you can do it 12 levels deep, a pointer to a pointer to a pointer to etc., to an int or something like that. Of course, why would you want to do that? I can't imagine why. But I have seen programs where you'll have double pointers. Oh, I've even seen them occasionally with 3 levels, but that's really uncommon, not terribly necessary. But it's not really unusual to have a pointer to a pointer. And I'll show you how to do that now. It turns out it's not as common in C++ just because of the type abstraction facilities of C++ allow you to define new types. And so often you'll only need one level of indirection for most usages. But anyway, you need to know how to do this, so here we go. This simple little example just extends an example we saw earlier. I'll define an integer I, and then I will define IP to be a pointer to an integer, and initialize it with the address of I. Now what I'm going to do is define IPP as a pointer to an integer, and it is going to point to IP. So IPP points to IP, which points to I. I know that sounds kind of funny. Oh well, that's just the variable names that I picked. Okay, so if I print out what the contents that IP is pointing to, well, that will be a 7, of course, because IP contains the address of I, which has a 7 in it. And if I print out what IPP is pointing to, its contents is the address of IP, which is 0012FF88, the address that was on the previous line. And then finally, I can use double indirection. If IPP is a pointer to an integer, then star IPP is going through 2 levels of indirection. The first level will take you to what IP is holding, and the next level will take you to what that is holding, which eventually, of course, gets you back to the original 7, which is in I. You can add or subtract an integer to or from a pointer in C. You may wonder why you would do such a thing, but if you're familiar with assembly language, this is not really unusual. It's just an offset from an address. So when you add a number to a pointer, what it does is it advances that address in memory, but it doesn't do it by a number of bytes, it does it by a number of elements. So for example, let's suppose I have a pointer P into an array A, and P is pointing to A sub 0. In other words, it's pointing at the beginning of the array. Then P plus 1 is going to be pointing at A sub 1. Another way to say that is that the address of A sub 1 is P plus 1. So, adding to a pointer moves that pointer in memory by elements. And that's why it's important that the system knows what type of object a pointer is pointing to. Otherwise, it doesn't know how far to advance it, because it advances by elements. Conversely, you can take 2 pointers and subtract them, and what it gives you is not the number of bytes between the elements that are being pointed at, but it gives you the number of elements between them. This slide and the next have an example which illustrates pointer arithmetic. I'm going to be using another type def, which is defined in the standard library. It's called pointer diff T, and that's a type which is used for the purpose of holding the result of subtracting 2 pointers. So it's a signed integer. One thing I wasn't really clear about on the previous slide is that when you subtract 2 pointers, it could be negative. It just depends the direction that you subtract them in. So anyway, the header standarddef.h has the definition for pointer diff underscore t, and you'll see that on the next slide. For now, just notice that I have an array A of floating point numbers, 1, 2, 3, and I'm initializing P to be a pointer to float with the address of A sub 0. So in other words, P is pointing at the first element in the array A. Now skip down to the first printf statement. First thing I'm going to do is print out the size of a float on my system. And the reason for that is so you can see that I will be advancing in memory by a number of elements instead of just a number of bytes. So the size of a float is 4. Okay, we'll keep that in mind. So now the next line will just print out the address which P is. It's holding the address of the first element in A, which is 0012FF80. And then the contents there, of course, is the number 1. Well, now I'm going to add 2 to P. P plus equals 2. That's going to advance P by 2 elements, which means that P should now be pointing at A sub 2, which is the number 3. And when I print this out, you can see that it is. And you can see more than that. You can see that the address has been advanced by 8 bytes. That's 2 elements of size 4. So this proves that pointer arithmetic advances by elements and not by bytes. Now what I'm going to do is illustrate the subtraction of two pointers. In that first line, I'm taking the pointer P and subtracting from it the array A. Now remember, the name of an array becomes a pointer to its first element. And that's actually true in all contexts except when you're taking a size of. When you take the size of an array, then you actually get the number of bytes in the array. So what do you expect P minus A to be? Well, remember, P is pointing at A sub 2, and A, of course, points at A sub 0. So since the difference is supposed to be a number of elements, we would expect that to be 2, which it is indeed. You can see on the bottom of the slide there. So that tells me how many elements there are between these two pointers. As far as the type of diff, remember I said it was of type pointer diff T. That is going to be some size of signed integer. If you want to see precisely what it is, whether it's a long or whether it's an int on your system, then just go into your header standarddef.h and find the type def for pointer diff T. Anyway, what I'm going to do now is I'm going to determine how many bytes there are between these two elements. Of course, I know what it's going to be. There's 2 elements between the 2 pointers, and 2 times 4 is 8. But I can explicitly calculate that in the program by casting each pointer to a character pointer. So notice what this does. The fact that I have changed the type of the pointer temporarily through a cast in that statement means that the compiler now is going to do different arithmetic. Since it knows that it points to characters now, at least that's what I'm telling it to interpret it as, it will give me the number of characters in between those 2 addresses instead of the number of floats, which was the intrinsic type of those pointers. So that's another use for casts. We can take this relationship between pointers and arrays a little bit further. Up until now, all we have said is that the name of an array becomes a pointer to its first element in most expressions. The notable exception of that is the size of operator. There's actually one more time where that is different, and that is with the ampersand operator. But that's a real kind of an esoteric case, and I'm not going to talk about it. So just keep in mind that the size of is the main exception to that rule. So every other time we expect the name of an array to be interpreted as a pointer. So another way to say that is that A is the same as the address of A sub 0. But now we're going to do a little algebra, as it were. If that's true, then I can take the contents of both sides, which will tell me that the contents of the address that the name A is pointing at is the same as A sub 0. But of course that's true. That's the way we defined it, so that's just kind of an identity statement. But now let's apply pointer arithmetic. In other words, A plus I is equal to the address of A sub I. Of course. Because adding a number to a pointer advances it by that number of elements. One thing I haven't stated too clearly is that this pointer arithmetic stuff that we're talking about here only applies when you're inside of an array. In other words, don't think that you can take a pointer to any variable and start adding to it when it's not inside of an array. It really isn't going to give you anything meaningful because a lot of platforms have memory alignment requirements depending on the type of variable that's being declared, and they may move things around and there'll be gaps in the memory. And so only within an array can you count on these pointer arithmetic things working. Anyway, moving on. The next line says star of the quantity A plus I is equal to A sub I. And that's a very important rule to remember. In other words, the contents of A offset by I is indeed the ith element of A. It's not a major revelation, I realize that. But if you will keep that in mind, you'll find that it'll help you as you use pointers. Now, that said, this last bullet shows you something really strange, which you should never do, but I'm just showing it to you for completeness here. Since star of a plus I is equal to a sub I, you could reverse the addition there and say star of I plus a is equal to a sub I, because addition really doesn't care which order you add things in. What that means is I can take an expression like star of a plus I and rewrite it as I sub a. Isn't that strange? And so it doesn't really matter whether you put the name of the array as the subscript or as the base array outside the subscript. Since it all boils down to pointer arithmetic anyway, and arithmetic is commutative, then they're the same. So what this does is it underscores the relationship between pointers and arrays. Nevertheless, notice the last statement there. Don't do it. That would be a very unfriendly thing to see in a program. This little program illustrates the relationship between pointers and arrays. It's the same min program that we saw a few chapters ago, but rewritten with pointer notation instead of array notation, at least inside of the function min. So notice that min takes a pointer to an int as its first argument. Well, what I used to have in the old version was int nums bracket bracket, meaning that it was an array. But remember, they're the same thing, at least in a function. When you pass an array as an argument to a function, you really just get a pointer to its first element. So I might as well just declare it that way and say int star nums. And so I will. Furthermore, I'm going to define an end of array sentinel value. In other words, I'm going to define an address which is outside the boundaries of the array. It's one past the last element in nums. And the reason I'm doing that is that becomes my sentinel address of when to quit. And it turns out that this is a very common idiom in C++. The algorithms in the standard C++ library use this very technique. So what we have here is we have a pointer which points one past the end of the last element in the array nums. Now, that may sound a little confusing because I just told you on the last slide that you can't go outside of an array. Well, the truth of the matter is that you cannot dereference a pointer which points outside of an array, pointer that originated from inside the array like this one. However, you can have a pointer point there, you just can't dereference it. So the C language standard does allow you to define a pointer like I'm doing with end here. Okay, well, having done that, then, I will, like I did before, I will take note of the first element in the array, which is star nums, because nums is a pointer to the first element. And then I will traverse the array by saying while plus plus nums is less than n. Plus plus nums will advance the pointer to the next element. And as long as that isn't the end pointer, which is right outside the array, then I'm still in the array, and I will continue in the loop. And so for the next line, I'll ask, is the current number I'm pointing at, star nums, less than small? If it is, then that's my new small, and I'll record that value. So when I'm done, I'll return small. Now, the question on the bottom, take a look there. What is size of A? Well, that's in the main program. A is an array. And so in the main program, the size of A is going to be, let's see, how many elements does it have? It's got 5. It'll be 5 times the size of an int, which on my platform will be 20 bytes. That's the size. What is the size of nums? Well, nums is just a pointer, so it's the size of a pointer, which again on this platform is 32 bits or 4 bytes. So do keep that in mind. Size of with an array only works in the scope where you have the definition of the array. Once you get inside the function min, Only a pointer has been passed. It has no idea what the size of the original array was. The things we talked about with multidimensional arrays are important to keep in mind when you want to have a pointer that points within an array, which happens to be a multidimensional array. And one of the reasons we're bothering to go through this is because this is extremely crucial when you end up doing the same thing in C++. This understanding is essential. So let's take a look at this example, a familiar example. We'll say that we have an array called A, which is a 3 by 4 array. Now you know what that means. It's an array with 3 elements. Each of those 3 elements itself is an array of 4 ints. So the size of each element is 4 times the size of int. That is the size of the outer elements, a sub I, for example, which on a 32-bit platform will be 16 bytes. So the question we have is this. Since we've just finished talking about how pointers can traverse through an array, pointing at each element in turn, how are we going to do the same thing in an array like this? In other words, how would I define a pointer to a sub 0 such that when I increment that pointer, it will point at a sub 1, the next element in the array A? Well, think about that for a minute. I know that it's tempting to want to say that it's a pointer to an int, but that's not true. What P needs to point to is the first element of A, and what type of thing is the first element of A? It is an array of 4 ints. So I have to define a pointer to an array of 4 ints. How do you write that down? Well, here's how you write that down. It's the third line inside of main. Now, what I have here is such an array. A is an array of 3 elements, each of which is an array of 4 ints. In other words, it's a 3 by 4 array. So I need to declare P as a pointer to an array of 4 ints. And if I had left those parentheses out on the declaration of P, then that would have said that P is an array of 4 pointers to int, which is not what I want. And so I've got to use the parentheses so that the asterisk binds more tightly to P than the brackets do. Looks kind of funny, but if you think about it, it follows the normal precedence rules of C that we've seen so far. So that's how you do it. Now that you have done that, we have declared a pointer which points at the first element at the outermost level of this array. What that means is that this pointer can now behave just like the array name does in any indexing context. So if you'll take a look moving through the program here, of course I'm going to use that idiom I told you about earlier, where I can calculate the number of elements in an array by taking size of A divided by size of A sub 0. That's the number of elements in the array, and I'm going to call those rows because that's a reasonable interpretation in this two-dimensional case. How many columns are there in the array? Well, that's equal to the size of the inner array elements divided by the size of the ultimate element inside those arrays, which is an int. You've got to think about that for a minute. The size of the entire array divided by the size of A sub 0, that's how many elements there are in A. But now we're looking inside one of those arrays, which is an array of 4 ints, such as A sub 0. And I divide that by the size of one of its elements, which is A sub 0 sub 0. That's the first int inside the two-dimensional array. That's a way of giving me how many columns or how many elements in each row. All right. And then I'll print out, of course, the size of star P, and indeed it is 16, as we guessed it would be on the previous slide. And then here's where you can see that I can use the pointer just as I can with the array name down in the printf statement inside the nested loop. I can say P sub I sub j. And that behaves just like A sub I sub j. But the only reason it does that is because I declared P correctly. I declared P to point at the first element of A, which is itself an array. I'm going to let you think about that for a minute until it sinks in. Well, just when you thought we were through with that multi-dimensional array stuff, here it is again. This is just to make sure that you're getting it down. By going through one more iteration here at the three-dimensional level, the pattern should emerge pretty clear. So, following what we did in the previous example, I'm going to define a three-dimensional array, a 2 by 3 by 4 array. But as you know, what the first element of that array really is itself a two-dimensional array. So I define P as a pointer to a two-dimensional array, which in this particular case, it's a 3 by 4 array of ints. So now, I can do what I did before. I will first calculate the number of elements in the entire array. I'm going to call it tables because that, of course, matches our geometric intuition with the three-dimensional array. It's a collection of tables. So, the usual idiom, size of A divided by size of A sub 0. Now, in each of those tables, how many rows are there? Well, the answer to that question is how many elements are there in, say, the first element of A. So I'll take size of A sub 0 divided by size of A sub 0 sub 0. And that gives me the number of rows in a table. Or in other words, the number of one-dimensional arrays inside a two-dimensional array, which is an element of A. Don't you love this stuff? Well, we're not done. Now we can get down again to the number of individual elements, which again, visually, we could call the number of columns in a row. But this time, I have to dig down deeper to that last dimension. So I'm going to look at the first element, that is the first one-dimensional array inside of the two-dimensional array inside of A, which is A sub 0 sub 0, and then I'll divide it by its first element, which is of course just an int. Anyway, hopefully you can see a pattern going on here. Now, because I've declared P the way I did, again I can use P as if it were the name of the array, and so I get things in the for loop just like I had before, but of course I have three dimensions since this is a three-dimensional array. Look on the next slide for the output. Well, I've printed this so that you can see what each element of A looks like. The first element is a 3 by 4 array, and the second element is another one. So those are the two elements of A. But inside each of those elements, being a two-dimensional array, there is a number of rows, each of those being an array. 0, 1, 2, 3 is an array. 4, 5, 6, 7 is an array. And then, of course, in each of those, we have the individual ints. So, you should be able to extend this to 4 dimensions, or any arbitrary number of dimensions, and as a matter of fact, that is one of the exercises. When you declare a pointer to an object, there are two things going on there. There are two variables involved. There's the pointer and there is the object it's pointing to, or the content, as we sometimes call it. Therefore, when you use const with pointers, there are two possible things that can be made const. One is the pointer itself, and the other one is the contents being pointed to. So, there has to be a well-defined rule to make that happen, so you can decide which you want to be const, and the rule is the following. It's where the const appears relative to the asterisk. In general, when a const appears before an asterisk, it means that contents is const. If it appears after an asterisk, that means that the pointer is const. And so the pointer can't be modified, but the contents can. If you'll take a look at the examples down there, and these are simplified examples. The rules that I just gave you work when you only have one asterisk. If you have more than one asterisk, it's a little more complicated to explain it, but I think you'll get the idea by just looking at these examples. With the first one there, const char star P1, that says that P1 is a pointer to a constant character. And so, since the const is over there with the char and not on the other side, not on the right side of the asterisk, that means the contents is const. So you can change P1. You could say plus plus P1, but you couldn't say star P1 equals some character because the contents is const. Now, just so you know, you can change the order of the keywords const and char, and that makes no difference whatsoever. Again, it's a positional thing. If the char and the const appear together in any order on the same side of an asterisk, then the const is modifying the char. Now, on the other hand, in the second line, you can see that the const is on the right-hand side of the asterisk. It's by the pointer instead of by the char. That means that the pointer is const, and so that's the inverse situation of the first line. The pointer cannot be changed, but the contents can. And, of course, if you wanted to do both of those, you could. Just put it in both places. Now, everything we've said about const as far as how it works, what modifies what, is identical for volatile. Volatile is another keyword. I'm not going to say anything more about it other than just to mention that volatile has to do with forces outside your program that may change it. You could have an address in mapped memory, which is, of course, mapped to some device, and so that device may have something happen to it independent of your program, and then that will change what's at that contents. And that's something called volatile. Anyway, suffice it to say at this point that syntactically, const and volatile behave identically. We've seen pointers to void once before, so it behooves us to explore them in enough depth to say we understand them. So the idea behind a pointer to void is that of a generic pointer. You're not committing at the moment what type of object you're pointing to. You just want to use it generically as a pointer to something. Later on, when you actually want to dereference it and get at some object, that's when you have to say what type it's pointing to. So it's pretty handy for things like containers. You can, for example, define a linked list which can hold void stars. And therefore, you can put anything in that linked list because those void stars can point to anything. But you're holding the pointers, of course, instead of the objects themselves. So it allows you to create a container without worrying about what type of object it's containing. So basically, you only have to write the container once, and it's pretty generic. The C++ standard library does a much better job of implementing containers, but this is still a basic implementation idea for such things. The rules are that you can assign any pointer to or from a void star. So if I have a void star, I can assign a pointer to character to it, and later I can take that same pointer and assign it back to a character pointer. However, if you do this in C++, you have to use a cast to go from void star back to some more particular type. And that's just your way of telling the compiler that you know what you're doing, that you know that what this thing is pointing at really is a pointer to char or whatever it was. In C, you don't have to do that, but that's one of the problems with C, and C++ is a safer language that way. Of course, if you have a void star, you cannot dereference it because the compiler needs to know what type of object it is to let you dereference it. It doesn't know how much memory to scan to let you use that object. So void stars are just for holding pointers, like in containers, or for parameters, as you've seen on various functions. This example takes a look at a function in the standard C library called memcopy. Memcopy is a function which allows you to copy any sequence of bytes from one place to another in memory. The first argument is where you're going to copy it to. The second argument is where you're going to copy it from. Notice it's a const void star. That says that source is a pointer to something that won't change. So in my program, I'll be changing source, or at least in one form or another I'll be changing source, but I won't necessarily be changing what it's pointing to. As a matter of fact, I won't be changing what it's pointing to. I'm just going to be copying it. But target is not declared const because I will be writing things at the memory pointed to by that. The third argument is the number of bytes to copy. So the reason this is a useful function is because you can pass any type of argument to memcopy, that is, a pointer to any type. It doesn't care. It's just going to trust you that the number of bytes is available to be copied, and it'll do it. And it does it by casting these pointers to character pointers, or in other words, byte pointers, because it's going to copy a byte at a time. So the first thing I do is declare a local pointer, target P, and that's a cast of target from void star to char star. And then I do the same thing for source, calling the local pointer source P. And now I can just have a loop that goes through for the particular number of bytes and copying from one place to the other using the standard C idiom. Star target P++ equals star source P++. So it takes the contents and copies it, and as a side effect, increments both pointers. So you can use this function by passing pointers to any objects that are compatible and the number of bytes. And so in the main program, just to illustrate, I'm going to take a float. I'm going to copy y to x. Now, of course, this is a silly way to do it. Normally, you would just assign x to y, but I want to show you how this function works. So this call to memcopy is equivalent to assigning y to x, because it's copying all the bytes of y to the bytes of x, and it does it by passing the address of x and y to memcopy and also telling it the number of bytes to copy. And so when we print it out, you can see that a 2 actually did get copied from y to x. This example also uses generic pointers, and to illustrate them, this time I'm using a function in the standard library called qsort, which stands for quicksort. Quicksort is considered the best all-around general-purpose sorting algorithm. And the way this function works in the C library is you give it all the information it needs to sort your array. You give it where it's at, how many elements there are, how big each element is, and you also give it a way to know how to compare two elements. So that brings us to the first line of the code after the include statements, which is a prototype. It is a declaration for a function which I have named comp, which stands for compare, and it takes two elements, two parameters. Notice they're both void stars, and they're const actually, because they're not going to be changed inside of this function. You'll see the code for this function on the next slide. Just keep in mind that its job is to do the comparing. So what's going to happen is that while qsort is doing its work, it's going to be looking at different elements in the array. And of course, it doesn't know ahead of time how to compare them. And so what it's going to do is it's going to pass pointers to the two elements that it is currently comparing to this function. And so the job of this function is to return some code, some value which will say, yes, they're already in order, or no, they're not, or whatever. Well, let's step through the main program. I declare first an array of pointers to character. So again, that's a ragged array. These aren't stored on the heap. They're stored wherever the system chooses to put them, which is the system's business, but it is an array of pointers. And each of those pointers points to a null terminated string. What I want to do is to sort this array. The next line, of course, is our familiar idiom for calculating how many elements there are in an array. So the number of strings in the array is the size of the array divided by the size of one of the elements. And then I call qsort. First argument is the name of the array, which becomes a pointer to its first element. So qsort is expecting an address for its first parameter. The second argument is how many elements are in the array. The third argument is the size of each element. And then finally, the fourth argument is that function, comp, which qsort will have to turn around and call itself. So comp has to be a particular type of function. It has to be a function that takes two pointer arguments. And since qsort is very generic, it can sort anything, then that compare function needs to take void star parameters. So once QSort is finished, then the array has been shuffled around and all of the elements have been moved, and now I can just print them out, and you'll see when we go to the next slide that they indeed got sorted. So here's comp, and its job is to return a negative number if the first element referred to by the first argument there precedes the second, in other words, if they're already in ascending order, or 0 if they're equal, or a positive number if they're out of order. In other words, if the element referred to by P1 comes after the element referred to by P2. And so that means they're out of order, and then QSort will swap them. So whenever this function returns a positive value, QSort will swap the elements. So you can have this work any way you want. I mean, if you want to sort things in descending order, then you would reverse the orientation of this. Put a negative sign in front of whatever you're returning, so it comes out reversed. So comp, of course, is written by you, and it knows what types of things we're comparing. That's the whole reason that we're doing this. QSort doesn't know, but it calls this function to do the right thing. By the way, we have a term, in case you're not already familiar with it, for a function which another process calls to get information in the course of its execution, and that's a callback. So comp is a callback, and what I have to do is I have to interpret these const void stars, which QSort has passed me. I have to interpret them properly as what they really are. Now remember, I have passed QSort an array of pointers. But QSort, what it does is it passes a pointer to the array element that it is currently looking at as the first argument to this function, and likewise for the second one. So what QSort is passing me is a pointer to a character. Now that should make sense to you, because if QSort can sort an array of anything, that means it can sort an array of really big structures. And there's no way it's going to want to pass those structures by value, so it always passes a pointer to whatever element type it's working with. So I have to take P1 and P2 and interpret them properly, so I have to cast them to what they really are. Since they're pointers to character, I will cast it such. And so I have a char star star cast in front of P1. And then what I want to do is I want to get at the actual element. I want to get at the pointer that is in the array, and so I have to do one level of indirection. In other words, I have to get at the contents of what P1 is pointing to. And I'll call that A. And so A is the actual pointer to character that represents my first string. Likewise for B, that's the second one. Once I've done that, all I have to do is pass those as arguments to string compare, because string compare does the right thing. String compare returns a -1 if A comes before B in alphabetical order, or it returns a 0 if they're equal and a positive if they're out of order. And so that does everything that I want to do. So just to summarize here, you are forced to receive parameters in this function as const void stars, because that's the way QSort is defined. Its fourth argument must be a function that takes two const void stars and returns an int. But you have to interpret those pointers as what they really are, because you know what is in the array. So you have to do a cast on those pointers. And in this case, since I have pointers to pointers, because that's the way QSort sends them to me, I have to do one level of indirection to get at the actual element in my array. And the actual element, of course, is just a pointer, but that's just what string compare wants, and so that's no problem. And again, if I wanted to sort things in descending order, all I would have to do is put a minus sign in front of string compare, and that'll return the negated value of whatever it computed. Anyway, as you can see, they're sorted. On the previous slide, we saw an example of a function being passed to another function. So you can pass functions as a parameter, but you might think, gee, how is that done? With data values, you know how they are passed. They are passed by value. They get copied onto the stack and used locally when you call the function. Well, it doesn't really make sense to copy a function's code and pass that. I mean, it's not really data in a C program. And so, how does it work? Well, the concept is that of a pointer to a function. And how it actually works, we don't really have to understand. Just the compiler has some mechanism of knowing that something is a pointer to a function. That's all it needs to know. And then it knows what to do with it when you use it. What I'm going to be showing you in the next example is how you can actually use a pointer to a function. In other words, if you were inside of QSort, how would you call that function? Of course, it's very simple. You just call it normally with normal function call syntax. So you just need to keep in mind that when you use a function as a parameter, the system just takes care of it. It passes it as a pointer to a function. You can even declare a variable to be a pointer to a function and to hold that, which we'll see on the next slide. So you don't need to explicitly use the ampersand operator to get the address of the function, nor do you have to use the indirection operator, the star, to use that function. This is a trivial little example, but its purpose is just to show you the syntax of how to use a pointer to a function. In this case, what I'm going to do is I'm going to declare a pointer to the printf function. Since I'm wanting to use printf, I have to include standardIO.h so that it is declared before I try to use it. Everything needs to be declared in C before you can refer to it. And if you look at the second line in main, here is where I am declaring a pointer to a function. Again, it's a kind of an unwieldy syntax. It's reminiscent of what we had to do with pointers to structures, but of course we invented a new operator to make that a little easier. But it's the same kind of thing. This line declares fp to be a pointer to a function that takes a certain number of parameters. Now, if I had left those parentheses off around star fp, then that would have declared fp as a function that returns a pointer to an int, and basically that would have ended up being a prototype, and that's not what we were after here. We are after declaring a pointer to a function, and so it always has to have these parentheses. So fp is a pointer to a function that takes a const char star as its first argument, and then an unspecified number of arguments after that. Now, this is a special concept, I realize. The ... is actually a language element. And the reason this is the case is because printf acts that way. You've used printf enough to know by now that you can have any number of arguments to printf. The first one is the format string, and all of the rest of the arguments are those things that correspond to the format specifiers in your format string. So printf is one of those variable length argument type of functions. So I'm just declaring fp to be a pointer to such a function. The bottom line is whatever the prototype is of the function that you're storing the address of, that's the way you need to declare the pointer. And if you were to look up in standardIO.h, the prototype for printf, you would see that it takes a const char star as a first argument and a ... as a second argument. Just for a piece of syntactic information, the comma before the ... is optional. But I like to have it. All right, now that I have declared fp as a pointer to a function and I have stored in it the address of the appropriately declared function, in other words, one that matches the declaration of fp as far as its arguments and return type go. Now I can call it, and I can call it in the normal way, the normal syntax of a function. I don't have to use the star to indirect fp, nor did I have to use the ampersand to store the address. Now you could do that, all right? You could say ampersand printf. That'd be all right. And if you wanted to, you could say star fp in parentheses followed by the arguments in a particular function call. But since the system knows that this is a pointer to a function, then it knows there's no other way it can be used, and so you can just use the normal function call syntax and it knows what you mean. I'd like to show you an example now that uses pointers to functions, just to show you a way that they're more commonly used. The previous slide was just to show you the syntax, but you would never really do that. So what we're going to do is we're going to have a situation, and I realize this is a little bit old-fashioned in this day of graphical user interfaces, but just suppose that we have just a text interface. We're going to print on the screen a menu for a user to choose, and there's 4 choices, and you're supposed to type in either the number 1, 2, or 3, or 4, and depending on the number that you type in, a certain function will be executed. So there'll be a retrieve function, say, whenever you press 1, an insert function when you press 2, etc. And when you press 4, we'll quit the program. What we're going to do in this example is have an array of pointers to functions so that I can read your number and use that as an index into this array of pointers to functions and just execute the appropriate function. Since the purpose of this example is just to show the mechanism of using pointers to functions, it's really not important for our purposes what exactly do the functions retrieve, insert, and update do. So I'm just going to declare them and assume that they're defined somewhere. We won't worry about them. But what I will do is I will define an array of pointers to functions, and that is the second line in main. F-array is an array of pointers to a function that takes a void as a parameter. In other words, it takes no parameters, and returns void. In other words, it returns nothing. And so these functions are strictly used for their side effect. They're functions that you call to do some action. And notice that I initialize that array using the normal, everyday array initialization syntax to be the functions themselves. Of course, it's the pointers that get stored. So retrieve, insert, and update in order are stored in the array F-array. It's important that those functions were declared. Otherwise, the compiler would not recognize retrieve. It wouldn't know what is it, what type of object is this. But since I previously said that retrieve is a function that takes a void and returns a void, likewise for insert and update, then it knows that these are functions, and they indeed match the declaration for F-array, for each element in F-array, and so it'll do it, and everything's just fine. So F-array is an array that holds these 3 pointers to function. Now what I will do is have an endless loop, so to speak. In other words, you can imagine this as a main driver program for this example. All it's going to do is it's going to show the menu on the screen, and we'll assume that's what the function show menu does. And it also, the show menu, will return your choice. And so the job of show menu is to clear the screen and print those menu choices and read your keyboard input. Likewise, we will assume that, well, actually, we don't have to assume that you're typing in the right thing. We'll just have show menu be kind of dumb, and it'll just print the menu and return your choice as a number. If you typed in a number between 1 and 3, then what I want to do is execute the corresponding function in my array, either retrieve, insert, or update. So I will simply execute that function. Of course, since arrays are zero-based, I have to subtract 1. For example, if you type in 1 for retrieve, that means that we really want to execute function sub 0 from the array. So all I have to do is say f-array sub choice minus 1 paren paren. Because f-array sub something, whatever the index is, 0, 1, or 2, is a function. More particularly a pointer to a function, but that's okay. As you know, I can use a pointer to a function with normal function call syntax, and so that's all there is to it. So here's a nice way of indexing into an array and just doing the right thing. I don't have to have an if statement that says, well, if you typed in 1, then call retrieve. Otherwise, if you typed in 2, then call insert, etc. And you can imagine that this could be quite handy if you have a very large number of functions. This code doesn't change other than certain hard-coded numbers, like 3 might be bigger and 4 would be bigger, but other than that, the logic of the program does not change at all. So arrays of pointers to functions can be pretty handy. Notice that if you type in a 4, I will go ahead and break out of the loop, and that will end the program. If, on the other hand, you type anything else any invalid number, such as 0 or a negative number or greater than 4. It just cycles on the loop and prints the menu again, and so as far as you're concerned, you don't really see a difference. In other words, you get no response until you type in a valid number. There's one last concept to cover that will help you as you go into C++ and try to understand objects and some of the good techniques for coding them, and that is a concept called an incomplete type. An incomplete type is a type which is only partially specified. You don't know everything about it. And there are really basically only two different categories of incomplete types. One is an array of unknown size. Now, we're actually not going to talk about that anymore after this slide. It's not that interesting. Basically, if you declare an array at the global level in one file, and you want to access that array from another file, you can declare something like this, extern int a, with empty brackets and not specifying how big it is. And that's okay. The system will let you do that. It will let you refer to this array globally. Of course, it's your responsibility not to go outside the boundaries of that array, but that's not germane to our discussion now. More importantly, the type of incomplete type that we will care about is a structure which has not yet been fully defined. In other words, it's just simply a declaration that a structure with a certain name exists, and it will be more completely specified at some later time. Now, you're probably wondering, why do we do this? Why don't we just declare the structure once and for all and get it done? Well, of course, you have to do that before you can use its members. But sometimes we may have a program, a set of functions, say, and all it does is use pointers to a certain type of structure. And in the declaration of these functions, for example, you're putting them into a header file, we don't need to know all the details about struct foo. We just need to know that it exists, and our functions are just taking pointers, receiving pointers to such a struct. The reason this is good is because the less information you put in a header file, then the less dependency you have on other information which is contained elsewhere, and therefore you may minimize the compilation dependencies that you have, and your compilation can go faster. It is also used with this concept of information hiding, which we've seen already, and which is a basic fundamental principle of object-oriented programming. So the example that follows will illustrate incomplete types, and I think you'll see why it's a good thing. The example we're going to use to understand incomplete types is an example that's always used for this purpose. And I suppose that we see so much of it, maybe we get tired of it, but it really is the simplest example to get the point across. And it's just basically the idea of a stack, which we've already seen. We're going to do this a little differently, though. We're going to use information hiding to its fullest that the C language allows us. The way we're going to do this is we're going to define a header as usual, stack8b.h, I'll call it. And in that header will be the declaration of the functions that a user can call to use a stack, to create a stack and push and pop and things like that. But the one difference that you will see here, as compared to what we've seen before, is that I'm not going to define the structure in that file. I'm only going to mention the fact that it exists. That way, there is less information. I'm trying to minimize the amount of information that I put into this header. Now, the implementation file will be in a .c file, and that is where I will give the complete definition of the stack structure. So here's the header file, similar to what we've seen before. The difference is that instead of defining struct stack, I'm only going to mention it. And as a matter of fact, I'm going to type def it at the same time. So when I say type def struct stack stack, the very fact that struct stack is mentioned, that's all that is needed to let the compiler know that such a struct exists. And of course the type def will, as you know, give it the name of stack in the normal variable type namespace, and so that way I don't have to keep repeating the word struct over and over again, which you can see in the rest of the file here. So for example, when I say stack create is a function that takes an int, which represents how big you want the stack to be, and it returns a pointer to a stack object, I don't have to say struct stack star like I did before, nor do I have to in the parameter declarations for the rest of the functions. This is the implementation file for these stack functions, and notice that, as usual, the first thing I do is include the header file where all the declarations are. Very important. You don't want any mismatches there. And here is where I define the stack structure. Now the user never sees this. That is, unless you give the user the source code. But commercially, that's not what happens. As you know, you as a commercial vendor would normally just give out header files with linkable libraries, and the user would never see this definition. They have no idea what the data layout of a struct stack is, and that's a good thing. That gives you that extra measure of information hiding that you want. This also turns out to be a technique that is commonly used in C++, so that the user, again, does not see the definitions of your classes, or equivalently your structures. You see, you may have some sensitive data in there. You may have some trade secrets. Who knows? You may want to keep secret how you do your implementation. And if you define your structure in a header file for all the world to see, that's going to give them a hint on how you did it. The other thing that this will buy for you, though, is that it's very possible that you may be providing layers of services. Maybe you want to define a more sophisticated data structure for your users to use, but it uses a stack in its implementation. Well, you don't want to have a knowledge of the stack data structure be in the header file for this new fancy whiz-bang data structure that you're doing. That increases dependency. Every time you want to compile in your build, you will also have to include the stack.h, and you don't want to do that. So by separating things as much as you can, that is separating interface from implementation, and using this technique of only mentioning the existence of a structure when it makes sense to do so, you can minimize your compilation dependency. So it saves you time in your development. And then, of course, the other benefit, as I've just explained, is that you can keep secret those things that you want to keep secret. Well, we've covered a lot of ground, and this really is the real meat of C. This is the hard stuff, and I hope that this presentation has clarified some of these difficult issues. But in summary, a pointer can refer to any C type, and there are two basic categories of types. There are data types and there are function types, and we have seen pointers to both. Remember that when you use an array, that the use of that name really becomes a reference to the first element in the array. In other words, for example, when you pass an array name as a parameter to a function, what really gets passed is a pointer to the first element. The key exception to this behavior is when you use size of in a context where the array has been declared. And in that case, you'll get the size of the full array in bytes. Const can modify a pointer, but it can also modify what it is pointing to, what the pointer is actually referring to. And you have that leeway. Sometimes you want to declare a pointer as pointing to something that itself is const, therefore you cannot change the contents through the pointer. Sometimes you want to declare the pointer itself as const and not what is being referred to. But the former is the more likely case. You usually declare a pointer to const. The idea of a void star allows us to have generic behavior. We can declare functions as returning, we can declare functions as having arguments, which are just generic pointers. And then it's not until we get inside of those functions where we interpret them properly. And as you saw, the main application of that is a callback. we passed a function to QSort, and QSort has no knowledge whatsoever of the things we're pointing to other than what we tell it. It's the function we gave it that did the important work. Also, we saw that you can use pointers to functions to use them as arguments to other functions, and that's basically what we did with our compare function to QSort. But also you can have, for example, an array of functions to pointers and use an index into that array, and that's pretty handy sometimes too. And then the last thing we talked about is that incomplete types support total information hiding. We can even keep secret from our users the very layout of our structs. There are 3 exercises for this section. The first exercise, I very simply want you to write a function called inspect, which takes a pointer to anything as the first argument, and then an int, I'm calling it size t, which is basically an unsigned int, which is a non-negative quantity, as the second argument. And what it represents, the second argument, is the number of bytes in the object pointed to by the first. What this allows you to do is it allows you to call inspect with a pointer to any type of argument, and the second argument being the number of bytes in that object. That is your first argument. And what I want you to do is to inspect each byte of the object that's being passed. So for example, I can call inspect with an address of a structure, and I just want you to print out each byte in that structure. By the same token, you could pass an int. And if an int is 4 bytes on your platform, then you will print out 4 bytes. And that way you can expect what's actually in each byte of that int, which is actually an interesting exercise. A lot of people don't understand that different platforms store the bits of an integer in different orders. Some of them put the most significant bit first, some of them put the most significant bit last. And you can find out what type of machine you have by passing an int to the inspect function and then having it print those out. Now, basically what you're going to have to do here is you're going to have to cast that pointer to a char star so you can look at each byte in turn. I would like you to print out each byte in hexadecimal, so use printf and have it print out with the X format. In this example, I'd like you to follow the pattern established in the stack program in this chapter and use total information hiding. I'd like you to take the employee problem from the previous chapter and reshuffle things around so that you only use an incomplete type for the employee struct in the header file, and therefore you will complete the type in the implementation file. So this will allow you to have the actual layout of your employee structure secret, and a user can't get at it. What that means is that these access functions that we defined, like get name and set name, things like that, become very important. Those are the only way a user can get at the information of an employee struct. The purpose of this exercise is to make sure that you understand the nuances of the relationship between pointers and arrays, and especially the concept of pointer to array. What I'd like you to do is just extend the 3D pointer to array example in this section to 4 dimensions. So if you understand the pattern there of how to have a pointer to an array and a pointer to a subarray, as we did, well then you'll be able to easily do this exercise.